Welcome back to the Dr. Stats-A-Lot channel series on probability theory. I'm Mark Ledbetter, and this is the second video for part 1, so video B, of section 5.1, which is titled Functions of One Random Variable, or we can call them transformations of one random variable. Now, in the first video, video A, we covered everything that was absolutely needed to do these transformations of discrete, finite, random variables. But in this video, we're going to do 3 more examples so that hopefully by the end of this video, the worksheet for this section and any other transformations of finite, discrete, random variables will be a breeze for you. At least that's the goal. So why don't we go ahead and get started. We begin with an overview of the lecture. So in this video, we're going to do 3 examples of how to transform the distributions of finite, discrete, random variables. We're going to use the same techniques we used in video A, and the random variables are going to be provided in table format. However, you may not always encounter finite, discrete, random variables in table format. Often, we're given a list of the values for the discrete random variable and their corresponding probabilities. The key is if there's a finite number of values for the discrete random variable, then you can put these distributions into table format and use the same techniques we're using here. Now, at the end of this video, we're going to review and summarize what we've learned for part 1 of section 5.1. And I hope that you have made the same observations about these 5 examples and analyzed them and looked deeper to see what's going on, the same as I have. And finally, here are the references again for this section because it's always good to give credit where credit's due. For example 3, we're going to start with a different distribution for x. This distribution is unimodal with the peak at x equals -1. It's also symmetric about -1. Now y consists of 2 functions that are both 2 to 1. The first is the absolute value of x, which is inside the second, which is a square. You're cautioned against trying to apply the graphing techniques learned in pre-calculus. We're not plotting y versus x. We're mapping x to y and carrying along the associated probabilities from x. So we plot x versus p of x and y versus p of y in the next slide. We start with the number line for x, and we map x to y using y equals 1/2 times the quantity absolute value of x minus 1 squared. Since this is a more involved calculation, let's walk through the first one with x equals -3. The absolute value of -3 is +3. 3 minus 1 is going to give us 2. Then we have to square that for 4. So 1/2 times 4 equals 2, and -3 maps to +2. Likewise, -2 and 0 both map to 1/2. -1 and +1 map to 0. Now, if the support of x included a +2, it would map to the same place as -2. Likewise, +3 would map to the same place as -3. So this transformation is symmetric about x equals 0. Again, the first table shows how each value of x maps to y and the associated probability that follows that particular path. Again, this is a working table, not something that should ever be presented as an answer, since it does not demonstrate a basic understanding of probability distributions. The purpose of this first table is to help us construct the second table. The proper probability distribution is displayed in the second table, and your answer should look like this. We use the first table to see that there are 2 ways to obtain y equals 0, namely x equals -1 and x equals +1, and also 2 ways to obtain y equals 1/2, which is x equals -2 and x equals 0. The probability for y equals 0 is obtained by adding 4/10 and 1/10, which is equal to 5/10. The probability for y equals 1/2 is obtained by adding 2/10 and 2/10 to give us 4/10. Notice that the total probability for y, again, adds up to 1. If the probability does not add up to 1, it is not a probability distribution and there is a mistake. So this is a good check. We now graphically explore the effect of this transformation. We started with the unimodal distribution x that is symmetric about x equals -1. The distribution of y is a strictly decreasing function. The effect of the transformation is provided to the right. The transformation is a 2-to-1 function. The absolute value took the non-negative of x and had 1 subtracted from it. The square skewed the values to the right away from 0, except for x equals -1, which went to 0. The transformation combined probabilities of x and resulted in a strictly decreasing function in y. In example 4, we choose a u-distribution for x, centered at x equals 0. We apply the 2-to-1 function y equals the absolute value of x plus 1. We start with the number line for x, and we map x to the absolute value of x plus 1. So we see that -2 maps to 1, -1 maps to 0, 0 maps to 1, 1 maps to 2, and 2 maps to 3. So the space of y is 0, 1, 2, and 3. Both x equals -2 and x equals 0 map to y equals 1. So the probability that y equals 1 is the sum of 5/16 and 1/16, which is equal to 6/16. Again, we compare the graphs of x and y to see the effect of the transformation. We started with the U-shaped distribution x centered at 0. The distribution of y has a sawtooth shape to it. The transformation is a 2-to-1 function. The first operation adds 1 to the value of x, which shifts it to the right. The absolute value reflects any negative values remaining to the positive portion of the number line. The combination of the u-shape to x and the absolute value function resulted in a sawtooth-shaped distribution for y in this case. Example 5. We use the same u-shaped distribution for x centered at 0. Here we use a slightly more complex 2-to-1 transformation for y. We map x to y equals absolute value of x plus 1 quantity squared. We see -2 maps to 9, -1 maps to 4, 0 maps to 1, 1 maps to 4, which is the same as -1, and 2 maps to 9, just as -2 does. So the transformation is symmetric about x equals 0, and the space of y is 1, 4, and 9. The probability distribution for y is provided in the table. We again compare the graphs of x and y to see the effect of the transformation. We started with the U-shaped distribution x centered at x equals 0. The distribution of y is strictly increasing. Now let's walk through step by step the effects of the transformation. The transformation is a compound 2-to-1 function. The first operation takes the absolute value of x, which reflects everything to the positive side of the number line. The next operation adds 1, which shifts everything to the right by 1. Finally, the square skews these values to the right away from 0, which stretches out the distribution. The result in this case is a strictly increasing function that is spread out across y. We have reviewed 5 examples for transforming a finite discrete random variable. Let's review what we've learned in this lesson. The key point for this lesson is that a function of a random variable is also a random variable. We've learned that a 1-to-1 function applied to a random variable will keep the general shape of the distribution. 1, it may reflect the distribution about the origin. 2, it may compress or stretch the distribution. 3, it may translate or shift the distribution. 4, it may do any combination of these 3 actions. Now, a special case of a 1-to-1 function is called the linear operator. It has the form y equals ax plus b. Now, if the absolute value of a is greater than 1, it stretches the distribution. Likewise, if the absolute value of a is less than 1, it compresses the distribution. If a is positive, the order of the distribution is preserved. If a is negative, the order is reversed. A positive value of b shifts the distribution to the right, and a negative value of b shifts the distribution to the left. Now, 2-to-1 functions applied to a random variable usually change the shape of the distribution, and they may also shift it. I hope you will agree at this point that it is very easy to find the transformation of a finite discrete random variable using this table method. Well, that's it for this video. I hope you've enjoyed it. Please make sure you complete the worksheet provided for this video. Remember that I always say that the only way to gain proficiency in a STEM, that's science, technology, engineering, or math field, is through practice. And just as you would probably not expect to win a race or win a game without practicing, it's not practical to expect that you can learn to do math and statistics without working these problems. When you're completing the worksheet, take that time to add whatever notes you need to your information sheet so you'll be able to do this in the future. Please stay safe and take care of yourself, because I hope to see you here next time.